What if I told you that the artificial intelligence algorithm predicting your next text message and the fluid dynamics keeping water flowing through your city's pipes, what if I said they both break down according to the exact same invisible mathematical law?
I mean, you'd probably think those two things have absolutely nothing in common, right?
Exactly. One is just, a digital brain made of code, and the other is actual physical matter moving through physical space.
Yeah. But when you push them to their absolute breaking point, the universe kind of forces them to play by the exact same rules.
It's honestly a profound realization. Welcome, learner, to your custom deep dive. Our mission today is to decode this breathtaking discovery about the architecture of stress and failure.
Right. Because we are so used to thinking about failure as a domain-specific problem. Like, if a bridge collapses, we blame the steel. If a market crashes, we blame the algorithms.
Yeah, we treat every disaster as this totally unique event.
Exactly, completely ignoring the fundamental architecture of stress itself.
So today we're looking at a pretty dense, cutting-edge, independent math paper. It's from March 2026 by a researcher named Michael Bird, straight out of Reno, Nevada.
And it is, well, it's the 13th version of this paper, so it's incredibly refined.
Right, and while you might be looking at the source material and just seeing, pages of intimidating equations, we're going to extract something that completely redefines how we understand fragility.
We're diving into this concept called universality.
Right.
And this paper actually originated from a very specific context. It was looking at prediction market diagnostics.
Ah, right, using the ether equation.
Exactly, the Aether equation.
Yeah.
But in analyzing that, the author uncovered a mathematical structure that has absolutely no known analog in standard fractal literature.
Meaning like not in the Mandelbrot set, not in the burning ship fractals, nothing.
Nothing. It's something entirely new.
Okay, so let's unpack this. The foundation of this whole paper rests on a specific mathematical iteration.
Yeah, think of it as a formula where a system is put under increasing pressure.
And in the equations, this pressure, this kind of stress style, is represented by a scaling parameter called K.
Right. So as you crank up K, the system gets squeezed harder and harder.
But to understand how these systems eventually snap under that pressure, we first have to understand how they move in the first place.
Which brings us to the first major breakthrough of the paper, which is the exact decoupling lemma.
Okay, yeah. So to grasp why this is so revolutionary, we need to picture how mathematicians usually map out complex systems.
Right. Imagine a standard 2D grid, like a piece of graph paper. The left-to-right axis is the real number part of an equation.
And the up and down axis is the imaginary part.
Exactly. And in almost all the beautiful, chaotic math we're used to.
What mathematicians call holomorphic equations, right?
Right, holomorphic. In those equations, those two directions are hopelessly tangled together.
Like if the system moves a little bit to the left on the real axis, it automatically forces the system to jump up or down on the imaginary axis.
They feed into each other continuously.
I read it's like trying to walk through a funhouse where tilting your head makes the floor drop out from under you.
That's a great analogy. And that continuous mixing is exactly what makes chaos so famously impossible to predict. You just can't separate the variables.
But this paper looks at non-holomorphic equations.
Yes. The author proves mathematically that for this specific family of equations under pressure, the two axes separate entirely.
The exact decoupling.
Exact decoupling.
So I was trying to visualize this earlier for you listening, and it feels like a band playing a gig. Normally, musicians are listening to each other, right? Playing off each other's tempo.
Sure.
But in this decoupled equation, the imaginary up and down axis is this incredibly domineering, autonomous drummer. They're playing their own beat, totally locked in, completely ignoring everyone else.
Right, and the real left-to-right axis is the guitarist.
Exactly. The guitarist can only react to the drummer's beat. They are entirely driven by the drums, but the drummer never, ever adjusts to the guitar.
The math behind why that happens is incredibly elegant, actually.
How so?
Well, the key is that the function of the imaginary part, which the paper denotes as little g of y sub n, is strictly real valued.
Okay.
So when you multiply the complex number by this real valued function, it simply doesn't mix the axes. The real part stays real, the imaginary part stays imaginary.
The drummer stays the drummer.
Exactly. The drummer stays the drummer.
But, why does that actually matter? Like, if I'm building a predictive model, why do I care that the math decoupled?
What's fascinating here is that it completely eliminates the need for endless, brute force computer simulations.
Oh, because normally mapping out the stability of a chaotic system takes massive computational power,
Oh,
right?
right. You just have to run the simulation a million times and see if it explodes.
Yeah.
But because the imaginary orbit, our domineering drummer, evolves completely autonomously, the author was able to derive a closed form formula.
Like a clean, perfectly solvable boundary.
Yes, a two-step stability boundary that predicts exactly where the system remains stable. It strips away all those unpredictable feedback loops.
Okay, so we have a perfectly mapped out safe zone. The system is moving predictably.
Right.
But that raises the core question of the whole paper. Now that we know how the system moves, what happens when we crank up the dial on the amplifier? Like, what happens when our pressure parameter, K, goes toward infinity?
The stable area, the safe zone where the system doesn't just spiral out of control, it starts to shrink.
But the mind-blowing part isn't just that it shrinks, it's how it shrinks.
Exactly. The strict geometry of the collapse, which the paper outlines as the fragility laws.
Right. So as K increases, the safe zone shrinks at a universal exponent called gamma.
And here's where it gets really wild.
Yeah.
This gamma exponent is dictated entirely by a single isolated trait of the underlying function.
It's vanishing order at the operating point.
Yes. They call this trait alpha.
Okay, let's define those terms for the listener, because
Yeah.
they're basically the linchpin of the whole discovery.
Sure. The operating point is essentially the system's baseline resting state under extreme stress. It's the critical juncture where the system is trying to balance itself.
And the vanishing order, or alpha?
It's a mathematical way of measuring how flat or sluggish the underlying function gets precisely at that balancing point.
Okay, wait. I have to play the skeptic for a second here.
Go for it.
Are you telling me it absolutely doesn't matter how complicated the system's underlying function is?
It really doesn't.
Like, you could have a massive ecosystem model with 100 variables, or a simple sine wave, and the only thing that matters is this single alpha value.
I know it sounds counterintuitive to ignore all that complexity, but that is exactly what the rigorous math proves.
It's like squishing a balloon, and the rate it shrinks under pressure depends entirely on the chemical makeup of the rubber, regardless of whether it's shaped like a dog or a sword.
That is a perfect way to put it. The macro shape ceases to matter when the pressure gets high enough.
Huh.
Only the micro properties dictate the failure. And to demonstrate this, the paper outlines 3 strict universality classes that every system falls into, based purely on that alpha value.
Okay, let's walk through these, because this is where the theory becomes like a tangible tool.
Right.
First, you have class A. This occurs when the alpha value, that flatness metric, is exactly 0.
Correct. When a system is in class A, the stable area decays purely as a power law. Scaling is k to the -2.
So as pressure increases, the safety zone collapses in a highly predictable geometric curve.
Yes.
So for you listening, if your system is class A, doubling the pressure doesn't just have your safety margin, it cuts it by a factor of 4.
It's a steep, punishing curve, but it is completely predictable.
Okay, then we have class B.
Class B happens when the alpha value is exactly 1. This is characteristic of functions with an odd 0, like a tangent hyperbolic function.
Right.
In this class, the fragility exponent gamma becomes 1, but with a crucial mathematical twist, a logarithmic correction.
A logarithmic correction. Can we ground that in physical reality? Because that sounds pretty abstract.
Sure, think of it like adding a parachute to a falling object.
Okay.
The object is still falling, it is still doomed to hit the ground, but the mathematical drag of that odd 0 slows the acceleration of the collapse just a bit.
Oh, gotcha. So it's a slightly softer landing than the brutal power law of class A?
Exactly.
Yeah.
The area shrinks proportional to the natural log of k divided by k, but it still follows a mathematically unyielding trajectory.
And then there is class C, which, honestly, reading the paper, this one felt like it was breaking reality a little bit.
Class C is incredible. I get really excited about this anomaly. This occurs when you have an infinite order 0.
Like the Gaussian function.
Yes, the classic bell curve shape,
Right.
mathematically written as e to the -y². In this class, the scaling acts totally bizarrely.
How bizarre.
The stable area shrinks at a rate proportional to a constant divided by the square root of the natural log of k.
Which is such a weird combination of terms. Square root of a natural log. Why does the bell curve behave so weirdly under pressure?
It comes down to how a bell curve is shaped. A bell curve never actually hits 0, right?
Right, the tails just go on forever.
Exactly. The tails get infinitely closer to 0 as you go further and further out left or right. So as you crank up the pressure parameter k, the operating point of the system doesn't just stay put.
That balancing point we talked about.
Right. The system has to run further and further out along those infinite tails to find stability. The operating point literally shoots off to negative infinity.
Ah. So because the balancing point is constantly running away from you, the collapse stretches out into this bizarre, anomalous, logarithmic scaling?
Precisely. It is a completely different qualitative behavior than classes A and B.
That's wild.
And we really should emphasize the rigor here. Michael Bird didn't just notice a pattern on a computer screen and guess these classes.
Right, he actually proved it. He solved the exact constants underlying these collapses. He resolved several open problems in the field, like OP1, proving the exact leading coefficient for class B is exactly 2r. He proved the exact mathematical footprint using tools like Euler beta functions.
Yeah, I saw that in the paper. He used Euler beta functions and Euler's reflection formula with sine functions. But how does a beta function actually crack a problem like this?
Well, in the realm of mathematics, an Euler beta function is essentially a translator.
A translator.
Yeah, it's incredibly good at converting chunky, step-by-step, discrete jumps, which is what our iteration equation is doing, into smooth, measurable, continuous areas.
Oh, I see.
By applying the beta function, the author bridged the gap between a chaotic, jumping algorithm and a perfectly smooth geometric area that we can calculate exactly.
Okay, so the math is undeniably beautiful in theory. You've got your drummer and guitarist decoupling. You've got your 3 universal classes of collapse.
But if you're listening to this on your commute or at your desk, you were probably wondering, does this abstract, complex number math actually map onto the real world?
Of course. That is the ultimate test of any theoretical framework. Does the theory survive reality?
Right. Do physical systems actually care about Michael Bird's universality classes?
Well, the author put this to the ultimate test. They ran the universal fragility laws across 8 different functions, spanning 6 entirely independent scientific fields.
Yeah, table 1 in the paper. This part reads like a crossover episode of all the major sciences.
It really does.
They tested an LSTM gate function, which is the memory architecture used in AI and neural networks.
Yep.
They tested a physics resonance equation, a control system's dead zone, a signal processing cosine, and they even tested a rheology yield equation, which models the physical flow of industrial fluids.
It's a phenomenal stress test. And the precision of the numerical verification is just staggering.
How precise are we talking?
Let's look at that rheology equation, the fluid dynamics model. That specific mathematical structure has an alpha value of 2.
Okay.
Based purely on that, the universality framework predicts a superlinear fragility exponent. The stability zone should shrink proportionally to the inverse square root of k.
Meaning, as the shear stress on the fluid increases, the safe zone, where the fluid flows smoothly without breaking into chaotic turbulence, it shrinks on a very specific curve.
Yes. And when they ran the numerical models, verifying this at a massive k value of 1 million.
1 million.
1 million.
Right.
The actual decay of the fluid stability matched the theoretical mathematical prediction to a 0.01% precision.
Wait, really? 0.01%?
It is practically flawless.
Yeah.
And they tested non-integer exponents too. Like an alpha of 3/4 perfectly predicted a collapse rate of 8/7, and that was verified to a 0.08% precision.
Wow. Let's make this real for a second. If you work in AI, you know what an LSTM gate is. It's what tells a neural network what information to remember and what to forget. And if you work in civil engineering, you know what a rheology yield equation is.
Yes.
What this paper is telling you is that when an AI model collapses under too much conflicting data and starts hallucinating, and when a physical fluid collapses under too much shear stress and turns into chaotic turbulence, they are dying in the exact same mathematical way.
Exactly. The underlying alpha value alone dictates the collapse, regardless of the physical domain.
That is just incredible.
And it isn't a gradual, muddy transition between these classes either. The system doesn't slowly morph from one set of rules to another.
Oh, right. The paper proves this with figure 1, the shifted tan experiment?
Yes. They introduced a manual shift parameter to a function to slowly slide the math from class B toward class A.
Basically, they created a slider dial to see what would happen in the middle space.
Right.
And if you look at the graph of this experiment, it doesn't slowly curve. The moment that slider dial hits exactly 0.25, the fragility exponent completely locks into class A.
The collapse rate becomes exactly 2.
It looks like a sudden, rigid mathematical cliff. The system just decides, okay, I'm a class A system now, and completely adopts those physics. There's no gray area.
If we connect this to the bigger picture, the implications are staggering. Whether you're studying the Ricker model in ecology or a neural network's memory gates, as you scale up that internal scaling parameter, k, the rate at which the stability collapses is mathematically identical.
But that raises a pretty terrifying question.
Okay.
We've established that the safety zone shrinks in this highly predictable universal way. But a shrinking safety zone implies you still have a safety zone.
Right.
Does the system just keep shrinking gracefully forever, getting infinitesimally smaller? Or is there a mathematical breaking point where it just gives up and shatters?
That brings us to section 7 of the paper, the final, most alarming discovery, the phase transition.
Because up until now, we've been talking about a predictable power law curve.
Right. For the exponential family of functions, our Class A baseline, that predictable power law decay, holds up perfectly as you initially increase the pressure. Okay. The safety zone shrinks smoothly, exactly as the k to the -2 formula dictates, but only until k hits roughly 25.
Here's where it gets really interesting. Think back to an engineering analogy. It's like bending a thick plastic ruler.
Yes.
As you apply force, which is our k parameter, the ruler bends according to a strict, predictable law of physics. You can map the curve of the bend perfectly.
Exactly.
But right at a specific threshold, right at k equals 25, the ruler doesn't just keep bending into a tighter curve, it violently snaps.
It is an absolute phase transition. Above a k value of approximately 25, the stable area completely stops shrinking as a power law.
What does it do instead?
It experiences a catastrophic exponential collapse. The data shows that the stable area literally halves every 2.5 units of k past that point.
So it goes from a predictable slope to essentially falling off a cliff.
Completely. At k equals 20, the safe area is 4.8. At k equals 25, it's 1.9.
Okay.
But by k equals 30, it is plummeted to 0.6.
Oh.
And by k equals 40, it is 0.04. It just vanishes.
Oh.
Now, the exact location of this transition, whether it happens precisely at 25 or somewhere nearby, depends on the specific constants of your unique system.
Sure.
But the qualitative structure of this absolute exponential collapse is universal across all the Class A functions tested.
So mathematically speaking, once you cross that threshold, your system is just gone.
Yes. And the paper goes incredibly deep to prove that this snap isn't just an illusion caused by looking at a simplified two-step simulation model.
Right. For those who love the deep nerd out, this is where the paper solved open problem 4 by mapping the crossover depths.
Yes, using something called the Lambert W function for two-step equations.
Okay, pause. I have to ask for a definition here. What actually is a Lambert W function for those of us who haven't taken advanced calculus in a decade?
Fair question. Imagine you are trying to solve an equation where your unknown variable x is trapped in two places at once.
Okay.
For example, x times e to the power of x equals some constant like 2. You can't just divide by x or take a logarithm to isolate it. Standard algebra fails entirely. The Lambert W function is essentially the ultimate mathematical crowbar. It's a specialized inverse tool designed specifically to untangle equations where the variable is locked in both the base and the exponent.
So Michael Bird took this mathematical crowbar, pried open the equations at k equals 25, and looked inside to see if the collapse was real.
Exactly. He used it to perfectly pinpoint where the system crosses over into collapse.
Yeah.
Furthermore, he proved that deeper n-step corrections are super exponentially subdominant.
Let me quickly translate that mouthful for you, learner. Basically, super exponentially subdominant means the math definitively proves that if you look further ahead, 3 steps, 4 steps, 100 steps into the future of the simulation, those deeper complexities are so tiny they are completely overpowered by the main rule.
Right.
They do not disrupt the universal law. The underlying mechanics of the collapse remain absolute. The snap at k equals 25 is real, and it is mathematically ironclad.
It is a rigorous defense of the theory. It proves the universality isn't an artifact of a shallow simulation. It is a fundamental property of the mathematics of stress.
We have covered a massive amount of ground today, and we've traversed some incredibly dense mathematical terrain. So let's pull it all together.
Sounds good.
We started with an intimidating non-holomorphic iteration equation, basically, a system under pressure. We discovered that by separating its moving parts, the domineering drummer and the reactive guitarist, we could completely decouple the real and imaginary dynamics on our 2D grid.
Which allowed for the discovery of strict mathematical laws, classes A, B, and C, laws that dictate precisely how the stability of these systems vanishes under pressure.
And it's all based entirely on the vanishing order, or alpha, at the system's operating point.
Exactly.
We saw how these exact same esoteric math laws govern the breaking points of artificial intelligence gates, fluid dynamics in mudslides, and signal processing models.
Universal laws.
And finally, we saw that even the most predictable systems have a hidden cliff, a phase transition around k equals 25, where the system stops bending and simply snaps.
Right.
So what does this all mean for you? Why does this dense March 2026 math paper matter to your daily life or your career?
It's a great question.
It means that when you are managing a complex project, when you are analyzing a volatile financial market, or when you are building an AI model, you cannot afford to get lost in the noise of your specific domain.
Right. Stop looking at the surface level details.
Stop obsessing over the shape of the balloon. Look for your system's alpha. Look for that underlying hidden structural trait that dictates exactly how fragile your whole operation will become when you inevitably turn up the pressure. Because the math proves that the pressure doesn't care what industry you are in.
This raises an important question, though. A truly fascinating implication to walk away with.
Oh.
We've seen the hard numerical proof that these exact mathematical laws govern stability, decay in ecology, fluid dynamics, and prediction markets.
Right.
But what happens if we apply this universal lens to even broader, messier systems? What about human psychology or macroeconomics or our political institutions?
Oh.
If societal stress is our real-world K parameter, as that stress inevitably increases, are our global institutions currently degrading on a predictable Class A power law?
That's heavy.
And if they are we nearing a phase transition? Are we approaching a threshold at k equals 25 where the stable area of our societal systems won't just smoothly decline, but will suddenly undergo an exponential, unstoppable collapse?
You hear the wood groaning. You can perfectly measure the bend of the ruler. The terrifying question is, do you know how close you are to the snap? Something to think about as you review the stress on your own systems today. Until next time, keep diving deep.